Okay, so hopefully you have submitted your assignment 1. The deadline was 11 a.m., half an hour ago. Usually, we don't accept late submission, okay, unless you have very special reason. So be careful, okay? So let me ask you a quick question. Is the deadline of 11 a.m. on Monday a problem for any of you? Is it okay? This I can change. For me, this is easy. I just change the time. If you don't want Monday, I can change it to Tuesday, for example. If you don't want 11, I can change it to 11 p.m. It's up to you. On Monday or on Sunday? (11:59 p.m.) Are you sure you want this kind of very unfriendly hour? No. Why is the no? There's a no. I need the complete set. Okay, Monday, 11:59. That's okay. That's completely okay for me. Is this something everybody wants? Just give me some indication so I have a. Okay. Okay, let me tell you the reason I said it on 11 a.m. That is because hopefully you will have submitted this and you come to my lecture, which is a fresh week. Okay, so you already finish everything and you come to my lecture and start a new week. So that is my reason of setting it at 11. So there's a educational purpose for doing this. But if you want 11:59, that's also okay. But then you run into if you don't understand the material set before, there will be a problem. Okay, so 11:59 is what you want. Can I confirm this? All right. Okay, but not from assignment 2. Okay, assignment 2 I already announced. There's 11 a.m. So you have to do it once more, 11 a.m. And from assignment 3, I will keep this in mind. I will set it to 11:59 p.m. But I encourage you to work on it earlier. Okay, and if I forget to do this, please remind me. I think I will be able to remember this. Okay, and the exercise classes, how was it last week? Last week, after our last meeting, you had the exercise classes. How did it go? How did that go? We had 3 slots. Any feedback for me? You can type, or you can type to me if you want. I just want to learn more about this. Why is it dangerous for all sessions to be run by the same TA? Now, the arrangement is this. The same TA will be in charge of the same exercise class of the week. Then they will rotate. They will rotate maybe week 4, you will see a different TA, but that TA will be in charge of the week 4. This is the best use of the teaching manpower. Okay. Do you have more feedback? If not, let me give you my feedback from my side. The attendance was not very good, and I was told you have like 5 students, 7 students on the second slot, and the third slot you had about 7 or 6. Okay, and again, I encourage you to join these exercise classes because you have some questions for you to play with. Okay, now the purpose of this is for you to discuss. Okay, I don't believe a given student will attend all 3 exercise classes. So if you notice some error, you will be able to sort this out. Okay, so if you spot something that you want to discuss, please talk to the TA. Actually, the way to run this exercise class is for you to do all these questions first. And my preference is for you to share your screen and do the question in front of your classmates. And then TA will give guidance. That will be my preference to run this. I don't know how practical it is. Okay, so I will talk to the TA again. But in any case, what we want is attendance, because we run 3 slots, and I would at least expect at least double of this number. Okay, that is also the reason why I ask you about the attendance of other classes. For my class, right now you can see I have 36 students, but this class, according to QC's last week, had 60 students. So this is at this moment when we have online teaching, I really need to make sure that we don't have students disappearing and we don't know. Okay, so now spread the word. If your friends somehow do not submit work continuously for too long, and sometimes we will analyze the attendance record. If we pick up some suspicious cases, we will try to contact the student. Okay, it's not because I'm interested to track you. I just want to make sure you are okay. All right, so last week we finished chapter 2. It's kind of good progress, and it's actually nice that we can finish almost one chapter a week, right? So last week was a little bit faster. And that's also because I had a little bit of time. I overran a little bit to finish the concept. So that will save me more time because I don't have to start everything again. Okay, so I apologize for that, but I think for you as a learner, you might appreciate this too, because when you watch the video, the whole presentation is more coherent this way. Okay, what did we cover last week? So last lecture, basically we talk about first law. Okay, what is first law? First law is basically some kind of conservation of energy when you take into account of the heat energy. Okay, so this will come back again and again and again and again. This is so fundamental. This is a conservation of energy. Okay, and today, very soon, you will see this again. And this is last week, and in particular, last lecture, we talked about heat capacity. So we talk about heat capacity at constant volume and the heat capacity at constant pressure. Okay, you will have a chance to practice how to manipulate partial derivatives and try to get some feeling about this. Okay, why do we care about this? Because this is a window for us. This is really an experimental window for us to test our structure of thermodynamics. So this is that's why this is important for testing the structure, in particular the mathematical structure of thermodynamics. You can do all this fancy manipulation, but are they correct? How do you know they're correct? What do you do? What can you measure? So these are some of the properties that you can measure. Okay. And the other thing we cover, very important, is ideal gas. I don't have a separate chapter on ideal gas. I could have done that, but instead I decided to spread this this content in different chapters. So whenever I have something I want to test, I will use ideal gas to test. And I will do it again and again. You will see it again and again. So ideal gas, we use it to test some of our derivation last week, which you have seen. And I also warned you in the notes that certain results, when it's not ideal gas, you have to be very careful. For example, it's worth to remind you again a few things. So for ideal gas, the first thing is the internal energy is a function of temperature only. And the other thing is, because of this result, the change of the internal energy has a very simple form, and this is related to heat capacity times dT. Okay, so this is only for the ideal gas. Okay, I already said it once, and I think it's worth to stress once again. This is only for the ideal gas. For other system, you might get this result, but that depends on the constraint. If you get this result for other system, other scenario, fine, that is okay. But for ideal gas, you can directly write this. And likewise, for other system, if you get this kind of result, you cannot claim that you have an ideal gas. So be careful of the logic. Okay, and then the next thing we did is we derive some result called some result for Joule's expansion. And we find that if you do this experiment, Joule's expansion, free expansion, using an ideal gas, you will get this result. So Joule's coefficient. Now, actually, there's a symbol for that. Last time I didn't introduce, but in my note, I have it. So this is eta. And this is defined as this particular partial derivative. Actually, I don't want to. Okay, this coefficient, I don't think we need to give this symbol because it's the same symbol as the efficiency for heat engine, which we will see today. So you just have to remember the Joule's coefficient is 0 for the free expansion. For the free expansion. So what does it mean? It means your internal energy is only a function of temperature, right? This is the same result as this. Another way to say that is we want to do this experiment to arrive at this result. And how do we do that? We do it by measuring the change of the temperature when you have free expansion. Okay, so this is something we did last time. And finally, we introduce something new. We introduce a new thermodynamic potential function, and that is the enthalpy. And I spent some time to convince you that this is not as artificial as you might suspect. You might say, okay, I just invent something to make my mathematics looks nicer. True, this is the case, but you already saw some application. You saw the application of, well, first, you want to have a parallel of writing this heat capacity as at a constant pressure. You want to write this in a nicer form, so we introduced this enthalpy. And you also saw how we use it to describe the flow, right? I have some fluid which I push through a plug, a porous plug, and I show you that the enthalpy in that case is the same before and after. Okay, and regarding this, I have some notes, some supplemental materials uploaded on Blackboard, and that is for you to see basically what I described at the end of my last lecture. So those are written in a short 2 pages notes from textbook. Okay, so you're welcome to look at that. And then it also tell you if you know how to write the internal energy. Suppose you know enough microscopic details, you know how to write the internal energy for the an element of fluid flowing through some tube, you can derive the Bernoulli equation. Okay, that part I also talked a little bit, but in the note is actually described for you. Okay, and this enthalpy we will see again. This is one of the four useful, useful, very useful thermodynamic potential function. Okay, you already saw two. Internal energy is one, enthalpy is one, and Gibbs function is one, and Helmholtz function is the other. So you will have four. We are going to look at the other two. Gibbs function, for example, is very important when you talk about phase transition. When we talk about phase transition, so from ice, the melting of ice, water ice, we will see this again. We will see the Gibbs function. Okay, so we have Gibbs, we have Helmholtz, plus the internal energy. Okay, so these are the four thermodynamic potential function you will see soon. Okay, so this is week 2, materials for week 2. And now week 3, welcome to week 3. What do we have to do now? Here, this is something very exciting actually, and it's also a little bit challenging. So from now on, this lecture, until I estimate about 3 to 4 lectures for this part. We are going to talk about second law. We are going to definitely talk about entropy, which is the hardest concept for this part of the course. And there are room for misunderstanding. And if the reasoning is wrong, the conclusion will be wrong too. Okay, so I want to do it rather, not too slowly, but I want to spend some time really to digest this together with you. Okay, so why do we need the second law? So first law, as we know, first law is about the conservation of energy. So first law deals with conservation of energy, and it tells you whether something, a change of the system, for example, is energetically possible. Okay, so this is the role of the first law. It tells you whether this particular process is energetically allowed. Okay, but that is not enough. For example, if you have heat flow, we always observe this. We can observe heat flows spontaneously from one temperature to the other. Okay, but if you reverse this, in principle, you do not violate the first law, right? So heat flow from hot body to cold body. If you reverse this and demand heat flow from cold body to hot body, this does not violate the conservation of energy. It does not violate the first law. But you do not see one of the two processes. Okay, another example, which is maybe quite familiar also, is the free expansion, right? This is the free expansion, Joule expansion. You have this partition, you have this gas particle originally confined to one side. So if you remove the partition, you have free expansion. This is okay. But if you analyze the energetic, if you try to put the partition in, you do not see the gas particle spontaneously flow to one part of the box, for example, the left container. Okay, although it doesn't violate the conservation of energy, this process just cannot happen. It just doesn't spontaneously happen. Okay, so this has to do with the second law. Second law will give you a way to deal with this. And this is also, sometimes people call this the error of time. So this is the error of time. So if you cannot tell the future from the past, you make yourself a box like this, and then you do the Fourier expansion. The future will have a box full of particles, and the past will have a box with particles confined to only one side. Okay, so this defines a direction of time. Okay, so Fourier expansion, the keyword here is this process. The reverse of the Fourier expansion does not occur spontaneously. Okay, maybe let's write this down. So Fourier expansion, the reverse of Fourier expansion cannot or does not occur spontaneously. This is the key word. So don't come and argue with me about this. One argument is this: if I cannot confine, if this does not happen, how is it possible that I can confine all the particles to one side of the box to begin with? Okay, what I want to say is I want some spontaneous process. If I want to prepare the experiment, that is not the same story. I can, of course, maybe put a pump and pump everything here, shut the valve and close the partition. I can prepare my experiment, but this requires my effort. This is not spontaneous process. Okay, and likewise, I can force the heat flow if I can do some work. Okay, so spontaneous is important. Okay, so here this motivates this kind of process. These processes motivate the need of the second law, or something more than the first law. So, okay, I will just write this for you. Okay, so one useful concept is the concept of heat engine. So heat engine, we already touched upon this when we discussed first law. So heat engine is a consequence of the first law, right? When you have the first law, if you look at the first law, you have these two terms, right? So here, I told you these are equivalent when it comes to conservation. So the natural questions that led people to the discovery of second law is, can I use some trick to convert heat to work? This is what I want. If I'm, for an engineer, what I really want is to extract some work. And can I maybe try to get some heat flow from the environment and convert this heat flow to something useful? Okay, and this is something related to, historically related to industrial revolution, right? How do I get more efficient? Right? Can I really come up with an engine like this? And the value of the first law is the following. Now, if you look at this, there's a step function here, which is the internal energy U. Okay, so if I want to have something useful, I want to be able to use it continuously. I want to, for example, drive a system from A to B and to C to whatever and back to A. Once I'm back to the same state, I can reuse the machine. This is the point. I don't want to build the machine every time when I want to perform the task. So if you have a machine or an engine that you can run in a cyclic fashion, then for every cycle, you will have internal energy to be zero. And that allows you to ask yourself, what is the efficiency of the conversion between the two? du is zero, so these two terms must balance itself. And that is the key question. Okay, and that is also, that reminds us about the origin of thermodynamics. Okay, really, back then when people thought about this kind of problem, they were looking at heat engine. Okay, let me elaborate these few lines a little bit more by this example. Okay, so I'm going to give you a reservoir. Okay, let's change color. This is nice color. Okay, this reservoir, I'm going to use it to dump some heat. Okay, so I'm going to connect this. I'm going to pick a reservoir with a temperature T. Okay, so heat reservoir. This is a heat reservoir. By definition, what is a reservoir? A reservoir is an object with infinite heat capacity. Heat capacity. That is to say, when I try to put some heat into this object or take some heat energy away from this object, I do not change the temperature because the heat capacity is so big that I cannot change the temperature. So T is a constant. Okay, so you can imagine a machine like this. I'm sure you can, everybody can. Okay, I'm going to make a machine or an engine to do this. I'm going to put some work and generate some heat. Okay, so this reservoir, for example, can be my head. And this machine can be a heater. And this work can be something I plug into the wall, the power socket of the wall. Okay, so everyone in this classroom can easily imagine a machine like this. Okay, so this is permitted by first law. I will have conservation of energy. The work that I extract from the power supply can all be turned into heat, and it will heat my head. That is okay. And this is something you observe in real life. Okay, now I'm going to draw this for you. Same thing. So this is, I'm going to draw it like that. This is the same T. This is some machine, which I will name it later. Now, what I'm going to do is simply reverse the arrows. So there are two arrows. I'm going to revert like that. Now, if this guy here satisfies the first law, this guy will automatically satisfy the first law because I simply change the sign. Okay, now what I'm going to do is to extract heat from the environment and hoping to get some useful work out. Okay, so let me write in different color, blue. So this is permitted by first law. Permitted by first law. And this one too, permitted by first law. Okay, no problem, right? No objection. I can do it this way. First law, this doesn't violate the first law. So this convert work to heat. This one convert heat to work. Okay, and this one is observed in real life. Observe in real life. And this one, now this is a key. This is impossible. This situation is impossible. So this is forbidden. And in fact, you will see the second law, this is the famous second law of thermodynamics, has so many different ways to state the law. And one of the statement is the so-called Kelvin statement. So this is related to Kelvin statement. We are going to talk about this later. This is a Kelvin statement. Basically, Kelvin statement say this is impossible. Okay, so I'm going to give a notation. And this is a machine. K denotes Kelvin. And this is a machine which is not possible. So I'm going to put a tilde. Okay, so this is a tilde K, which means this is a machine which is hypothetical, is impossible. Okay, so this is forbidden by what? This is forbidden by the second law. We need another law to tell you this machine is not possible, and this machine, if we construct it this way, is related to Kelvin's statement of the second law. Okay, I don't want this here. I will just write it a little bit better for you. Okay, so now you see the point, right? And in order for this kind of process, a similar process to work, you do need something else. What is the something else? So this is not possible. What is possible? The thing that is possible is you will always have another reservoir to dump the heat. This is possible. Okay, so this will be a heat engine, no problem. And without this part here, is not possible. Okay, so if you add this, I don't know how to write this. If you add this part, then it's a valid. So the heat engine is permitted. Is permitted. If you add this, when the reservoir T prime is included. Okay, and this T prime here is called the thermal waste. And think about this, what does it imply? There is another statement of the second law. This is all related. Another statement of the second law basically says something like this: you cannot have a machine which is 100% efficient, right? So if you have all the heat, you are able to extract. If you can convert all of them to work, you have 100% efficiency. So the second law basically say, no, this is not allowed. You won't be able to do this. Even if you are the smartest engineer in the world, this is not possible. Okay, so you will always have some waste, and we model this by connecting the thermal waste to another reservoir. Okay. Now, just for fun, I want to present this to you. And this is very cool. This is very old, and it's kind of romantic when you see this kind of picture in a modern textbook. This is this heat engine is kind of easy to understand, and you can really see what people are thinking. Right? You are really trying to extract work out from a machine by injecting heat. Okay, this is a simple machine for you to understand, and it's not as idealized as before, but you can see what is the purpose here. Okay, these two are basically the same picture. I found online. Maybe the one on the left is the original drawing, and the one on the right is the schematic, which is easier to see. Okay, I will take you through this. What is the purpose of this? The purpose of this is to get some work, extract some work out from this device, so you can pull some mass. For example, a very heavy bucket of water from the water well. Right? The idea is you want to pull this. And how do you do that? Okay, you can initialize it like this. So here, let me take you through. This is this thing can swing about this pivot point. Okay, so it can rotate like this. It can turn like this. And here is some kind of piston. This is your piston cylinder system with some gas. Okay, so you can imagine this pink color to be the vapor of your liquid. So suppose this is water. Blue one is water. What you do is you heat up the water. So when you boil this water, you create a lot of vapor. Okay, so you open this valve here. There's a valve, and you let this vapor goes into your cylinder, this tiny chamber here, and this will expand, and it will push the piston up, and there's a counterweight here, so it will go down. So this is for you to initialize it. Okay, so this piston will go up and this will goes down, and then you have a hook, for example, and you can put your bucket here. Okay, this is the initialization. And the next thing you do, once you are ready, you ask your friend to open this valve, and this valve contains another tank of cold water. And this cold water will flow inside, and this is cold water, and this is hot vapor. Okay, so the temperature change will be such that all the vapor here will be condensed. Okay, this vapor will be condensed because of the cold water, and it will drip back to the bottom. You can turn off the heat, for example, or instantaneously you can imagine what happened. And once it's condensed, pressure drops, and the atmospheric pressure will push the piston back down, and you can use it to extract useful work like this. Okay, so this gives you a very simple concept of heat engine, and it's not very efficient because you then have to reheat the water, refill the tank, or you can build some structure to run it in a more efficient way. But this is to convince you that heat engine is not just a thermodynamic toy. It's something that people were thinking for a long time, right? The purpose is to get work done. All right, so let's move on and look at the heat engine. I'm going to consider the heat engine, an idealized heat engine like this. I'm going to have two reservoirs like this. And for this chapter, I will also want to reserve the symbol theta. So this theta is the temperature. So this, I don't want to use T, because one purpose of this chapter, later part of this chapter, is to establish the thermodynamic temperature scale. And that is, for that scale, T is a symbol we use. Okay, so for now, although if you have seen this material before, you know eventually this will be the equivalent stuff. But in order to prove it, I want to reserve the symbol T for that purpose. Okay, so think about this as the temperature. So this is the temperature of the reservoir here. Okay, so the constraint is this is the higher temperature, higher than the cold reservoir. So this is a hot reservoir and this is the cold reservoir. Okay, so a typical heat engine you have seen earlier, I will also label it for you. So I'm going to take the heat coming from theta 1. I'm going to use a symbol Q1. And then the work extract will be W. And we know this, if you stop here, this is not allowed. So we need to connect the waste. This is the thermal waste. And I'm going to label it Q2. Okay, and this is a machine that I'm going to operate in cycles. So after the cycles, it will return to the initial state. And then you can use it again and again and again. Okay, most machines will be very complicated. For example, if you if you look at the car engine, that is very complicated. But we can study some idealized ones represented by this. And one of the most important engines will be the Carnot cycle. Okay, so here this is an engine which is allowed. So I'm going to name the engines later. Okay, you see a lot of diagram like this. Okay, Carnot cycle is the most important. Let's see whether I have the next slide. This is the Carnot cycle. Actually, it would be nice to put these two together. Give me a moment. I think I can. This is here. This one, yeah. Okay, so I'm going to discuss a Carnot cycle. Can this be moved? Very bad idea. Sorry, it's not very tidy, so I'm going to put it here. Okay, this is a Carnot cycle. We learned about this last week. And a Carnot engine. A Carnot engine. What is a Carnot engine? It's an engine based on a Carnot cycle. Sounds a bit stupid, but that is the definition. And this Carnot cycle has two isotherms and two adiabats, and as labeled here. And so I will tell you which one. So if I go from A to B, A to B, and also A to B or C to D, these are the isothermal process. And this isotherm will be at theta 1 and theta 2 respectively. So these are related. And if I go from BC to DA, these are the adiabats. So the process is adiabatics. No heat can enter. Okay, so if I go from A to B, what happens is last week you already showed, if I have this isothermal expansion, you know heat will enter. So this is Q1. Okay, this is the same as this. This is Q1. And if you do an isothermal compression, that is from C to D, from C to D, heat will leave the system. So this is Q2, and this is this Q2 here. So it's not too crazy. If you have a PV system, this is something you should always use to imagine the situation. I'm performing isothermal expansion at theta 1. So if you look at the engine, this diagram here, I'm injecting heat at theta 1. And the amount of heat I inject is Q1. Okay, and what about work? Why is this work done? This work, I'm going to, the work per cycle will be related to the difference between Q2 and Q1. Why? Because of the fact that when you go back to the same point A, U is a function of state. So the work you get has to be balanced by the heat flow, whether it's in or out. Okay, so the work per cycle is related to the difference between Q1 and Q2. Okay, so these arrows are all, they all make sense here, as far as first law is concerned. Okay, let me tell you what is the work. Work will be if you go along the cycle, a closed path. For the PV system, this will be the work. Okay, I remember, you see, I put the absolute sign here. So if you go from A to B to C to D to A, this area enclosed by these lines, these curves, will be the work done. Okay, so for this part, please be careful of the sign convention. If you read all these textbooks, they all seem to, it doesn't matter how they define the first law, whether they define d bar W to be positive or negative, they always like to, and this is a standard way to draw the diagram. Okay, so in other words, this is really the work done by the system, right? Because we are always talking, when we first introduce first law, we say d bar W is positive when you have a work done on the system. And now when you draw it this way, and somehow people like to use positive sign, and that's why, in order not to confuse people, if you know what you are doing, if you draw the arrow the way it should be, very often people just mean the absolute value of work. So this is something you need to be very careful, and you need to think about this. And in my notes, I make sure I check again to make sure the sign convention is correct this way. Okay, so there's no danger of the minus sign. So you have to be careful what it meant. So when I talk about work per cycle, okay, I will write more. This is work per cycle. Work per cycle. And sometimes you see this. You have this heat coming in. Half of them, some of them will be converted to work. Some of them will be converted to the waste. So the difference will be the work per cycle. Okay, but you should always be careful. Here, what we really mean is this. Okay, so this is when the arrow is drawn this way, this is the work per cycle. Okay, so be careful, be careful. Be aware of the real meaning of the sign convention, real sign convention. Okay, it's not that difficult. Actually, it's kind of intuitive if you look at it this way. But if you want to have a very coherent presentation of the note, sometimes you really have to think a little bit about how to write it out mathematically. Okay, so in the note, I will also use Q1 minus Q2. If you read Steen, he also did Q1 minus Q2, but the real meaning is because the sign convention is really absorbed by the direction of the arrow. Okay, so here we are going to define the efficiency. So the efficiency, eta, is defined as the amount of work you can extract divided by Q1, which is the heat you inject. Okay, so this is what you get, this is what you pay. Okay, this is how you define the efficiency. But again, let me remind you, this really means the absolute value of W divided by the absolute value of Q1. Okay, and then what is Q? What is W? W is Q1 minus Q2 divided by Q1. And therefore the efficiency is this, 1 minus Q2. 1 minus Q2 over Q1. Okay, if you have a heat engine, you want the efficiency to be as high as possible. And how do you get as high as possible? Now, one scenario would be this. You can consider setting Q2 to be 0. If Q2 is 0, then you have 100% efficiency. Okay, you think this is a very smart move, but unfortunately, this is forbidden again. We already saw this. If you set Q2 to be 0, that is to say you block this path, then you will have efficiency of 100% efficiency. This is not allowed. Okay, so this is, if you do it that way, you have this heat engine, which we call not K. Okay, so at this point, we should introduce the statement formally. So I'm going to give you 2 heat engines. So this we don't want anymore. Here. Okay, there are 2 kinds of heat engines. They are related to second law. And I'm going to use this again. 2. I want 2 of them. Good. Okay, these are the 2 impossible engines. Impossible because it's forbidden by the second law. That's to say, from this formulation, I can state 2 statements of the second law. So the first one is like this, you already saw, right? Convert all the heat exclusively to work. So this is not allowed, this is not K. Okay, not allowed. Remember, I will be consistent with this symbol. The other one which is not allowed is here. This is also not allowed. If you only try to extract heat from the cold reservoir and then all the heat get transferred to the hot reservoir. I should write Q1, but in this case, Q1 and Q2 are the same. Whatever you do, you have to respect the first law. So if you take all the heat from here and you don't do any work, then you have to send all of them back to theta 1. Okay, this is also not possible. This is not C. This is called not C. Okay, so these are the two statements of second law, and I will give you the word now. Then we can take a break. Okay, this is the two statements. Okay, so these are two statements of the second law. So this is Kelvin's statement of the second law. And this is the closest statement of the second law. Okay, I will call for a break now, a short break. 5 minutes, come back at 12:31. And please spend some time to look at this diagram and admire the writing, the words, yeah. Okay, and later I'm going to prove the equivalence of the two. Okay, all right, so let's take a break, come back at 12:31. Okay, welcome back. Okay, so before the break, I presented these two engines. These are the impossible engines. That's why there's a mark here, just to tell you this engine is not possible. But it's very useful for us to make some progress. Another thing I want to say before I forget is about the Carnot engine. The other thing we should, so if I go back here, this is Carnot engine is based on a Carnot cycle. Okay, another way to say that is the following. So I'm going to put a star here. So a Carnot engine is an engine which is reversible. So a Carnot engine is always reversible. So I will write it this way, is reversible. So the statement is the following: if the engine is reversible and you only have two reservoirs and the two reservoirs are really at constant temperature, and this is a Carnot engine. So I will write it slightly differently, as Carnot engine is reversible and operating between two reservoirs with constant temperature, with constant theta 1, theta 2 only. Okay, so this is a Carnot engine, and later we are going to use this engine to get a more general result. We are going to imagine a very complicated engine with many different temperatures, and we are going to take advantage of our knowledge of Carnot engine, and eventually we are going to use such a setup to derive a very famous theorem, and that's Clausius theorem. Okay, so this is something we will we will try to do. So I will also say this is useful, eventually useful for this, for the full derivation of a very general case. Okay, so here we want to show that these two are equivalent. We want to show that these two are equivalent. And how do we do that? Can we move? Yes, we can move a bit. If we want to show two things are equivalent, we have to show two directions. So one is we show a not C implies not K. Okay, and this is what I will show. But if you only show this, this is not enough. But after all, these are both the statement of the second law. So they should be equivalent, and you should have a way to show that they are equivalent. So I'm going to show this direction, and then you are going to show this direction. So this is you, and this is me, and this is you. Okay, so I'm going to show number one for you. And once you show that, you can say these two statements are equivalent. And this is a very standard trick. We have a lot of ways to get some powerful statements like this. So this is the starting one. Okay, show this imply this. Okay, not C imply not K. Okay, what do we mean by this? Again, we are going to take some engine. So I'm going to take this engine again. How many? I need 2 engine. Okay, now I'm going to put them side by side. I cannot place side by side. Okay, this is annoying. Okay, one engine is, we want to start with not C. So I'm going to put the not C here. So this is my engine, which I assume it exists. Okay. And then I'm going to drive it with a normal engine. So this is a normal engine. I'm going to give the symbol N. Normal engine is allowed by the second law. And this is an engine which, according to our statement of the second law, is not allowed. It's not possible. Okay, and I'm going to convert. I'm going to put this really next to each other. Okay, so this is really the same. The reservoir temperature is really the same here, and likewise here. Okay, so the normal engine will operate normally. So I can take my heat Q1, dump my heat Q2, and extract word W. You have seen this at least 3 times today. Okay, so I will quickly write it as the difference between the two. Okay, so this is just a very standard setup. You see the arrow is pointing this way. This arrow is going into this machine. So the difference Q1 minus Q2 will be the heat that we can extract. And the not C is an engine that takes all the heat here and dump the same amount of heat here into theta 1. Okay, this is shown here. This one. Okay, now you have to be careful. I'm going to label this Q2. Okay, so you need to think a little bit. Let me label first and explain. So this is Q2 and this is Q2. Now, what is the thinking you need to make? You need to really think through. What you have to do is to make sure I can use the same symbol for these two. This is Q2. I already used Q2. Why do I not call it Q2 prime? Why do I do it? Why do I write Q2? The reason is this. I can always drive my normal machine. I can always adjust the rate such that for the given duration, say in 5 minutes, I want to dump exactly the same amount of heat as the heat, this hypothetical, this not C machine will extract in the same 5 minutes. So that is to say, this kind of engine gives me this flexibility. So I can always arrange this to be the same as this. Okay, so once I do that, this is Q2, this has to be Q2. I fix this machine. Okay, so I have these two machines. I'm going to put them together side by side. That is to say, I really merge the reservoir. So this is the same reservoir. I'm going to dump the heat into this reservoir, and from the same reservoir, I'm going to extract the heat Q2. Okay? Okay, if you look at this, what do you learn? What do you learn from here? What you learn from here is, if you consider this, now you draw a black box here. Suppose you don't know the internal arrangement of the composite machine. This is, you can look at this as one single machine, right? So you can look at this as a composite machine. I'm going to really show you. We are going to consider this as a composite machine. And what do you extract here? So this is my composite machine. Composite. Okay, so from this composite machine point of view, I have this Q2 go in and then Q2 goes out. So there's no Q2. Okay, and if I draw the arrow downward, what do I have? This downward is Q1. So I have to have the difference of Q1 minus whatever heat energy that I send back to theta 1. Right? I draw the down arrow like this. Okay, and now you know this is a real disaster, because now this work, I already told you the work is Q1 minus Q2. It doesn't matter whether we draw it as composite machine or what, because there's only one output if you draw the composite machine. And this output is Q1 minus Q2. Okay, and this is a scenario I say is impossible right from the beginning. Right, so this is a work, this is work. So I convert all the heat 100% to work, so this is not possible. And this is equivalent to not K. This is essentially a not K. So I prove to you that if you start with a not C, you end up with a not K. Okay, so this is case 1. And similarly, you will be able to arrange a scenario for proving the opposite direction. And once these are proven, you have what you want. So this is this is exercise. Okay, so now the next thing we can do is to discuss a little bit about this efficiency, this issue of efficiency we discussed earlier. So earlier we talked about the efficiency of a heat engine. So this is given by this symbol eta, and this is what you get over what you pay, and you end up having this Q2 minus Q1. Okay, as usual, I want to get more feeling by considering a case which is more familiar. Okay, so I'm going to consider a Carnot cycle. I'm going to consider this engine, so consider a Carnot engine with ideal gas as the active substance, or sometimes people call it the working substance. Okay, and that is again this figure, but now you can do a lot more, right? Now it's not just a random PV system. Now it's a PV system which you can write down the equation of state. Okay, so again, this is a specialized case. This is not as general as before, right? Because I demand this to be an ideal gas. Okay, the result we already know because we spent time to do this last week. So from A to B is an isothermal process. Right? From A to B is an isothermal process. This is the dotted line, blue dotted line here. Right? Remember, this is an isotherm because when you look at B, the adiabat is always steeper. So this is the solid line is the adiabat. Okay, so I don't want to calculate again, but we know the Q1 can be written as R. So this is, with one more, I want to suppress the little n. So Q1 is R times theta 1, the temperature at the reservoir, and log Vp divided by Va. Okay, you have seen this, and you will have no problem to calculate this. Okay, what about from B to C? B to C is adiabatic. This is adiabatic, and we can get some useful relationship because I already know what I want. I will just write it down. This is turns out to be the ratio between the two temperature, right? You go from B to C. B is at theta 1, C is at theta 2, and you ask yourself what is the ratio of the temperature. And this turns out to be related to Vc divided by Vp raised to the power of gamma minus 1. Gamma is the adiabatic index. Okay, and this point, and then C to D is just the reverse. Right, so you have isothermal compression. So now you're operating at theta 2, isothermal process at theta 2. You have log, this is from initial to final. So final is D, initial is C. So I can just copy all the expression. Now at this point, we write it in a way that respect our sign convention, and you will be able to check quickly that Q2 indeed leaves the system and Q1 enters the system. Okay, finally from D to A, you go back to adiabat, and this gives you the ratio, another useful ratio. Okay, theta 2 divided by theta 1 is VA divided by VD, gamma minus 1. Okay, exercise. Not very long. So you can show that you have Q2 divided by Q1 is the same as theta 2 divided by theta 1. Okay, and in order to get this correct, now you see if I really use the sign convention of when the heat leaves, I have minus sign, then this will be a minus sign. So this really means the absolute value of Q1, okay? And that turns out to be the ratio of the temperature. Okay, very important, this result. This is can show. Can show means you should show, really. This is important result. Okay, so when we want try to calculate the efficiency, you see we have this ratio here. Now heat energy may not be easy to measure, but in the end, this is nothing more than just the ratio of the reservoir temperature. So I can kind of imagine how to drive an engine which is very efficient. I can simply change the temperature of theta 2, right? I can make it as small as possible. So this term will be as small as possible. So my efficiency is as large as possible. Okay, that's why sometimes when you see people running engine, they like to have the outlet at a low temperature. For example, if you are talking about some kind of a big structure that requires a lot of cooling, they build it next to a river. They use the water temperature to regulate this as the water becomes the reservoir. Okay, so this is something that can kind of have a better feeling about this, and then they adjust the temperature of the high temperature reservoir, and that is the way they control the efficiency. Okay, since we're talking about the ideal gas, I want to give you one more presentation. Again, this is for ideal gas, for an ideal gas. For an ideal gas, there's another way to look at this, and that is we start from first law, du is d bar q plus d bar w. Okay, what can I do? What I will do is this. Okay, let me change it. Change the subject like this. So I have du minus d bar w. I'm going to divide by temperature. By some temperature. Okay? And I'm always allowed to do that. And now I'm going to imagine my working substance, my ideal gas, is enclosed in my piston cylinder system. So I can use the PV system to model it. So for PV system with ideal gas, then the next line becomes du plus PdV, right? This d bar w is minus. Okay, so actually so far, this is a PV system. So I would just take it one more step for you. So from here to here, this is a PV system. So I can write the way to perform work. And then this is PV system plus ideal gas. Now, what do we learn when we have an ideal gas? Again, one more of ideal gas. What we learn is the following. We learn from Joule's expansion. We learn from the recap at the beginning of today's lecture that U is only a function of temperature. So I can write something like this. I can write du d theta and change it to d theta. Okay, the reason I can do this easily is simply because this is U is a function of temperature only. Okay, so this is also reflected by the fact that I do not use partial derivative. And now I have P divided by temperature. And I know my equation of state, that is R divided by B, dV. Okay? All right. So what do I gain by this exercise? So here, this gas constant is a constant, and this whole thing is a temperature of volume only. It's a function of volume only. So this is function of V only. This is temperature. U is a function of temperature only. So this is also function of theta only. And both temperature and volume are function of states. Okay, so it means if I integrate the right-hand side, so if this means if I integrate the right-hand side, I must get 0. If I integrate around a closed path, It has to be 0. Okay? Now, right-hand side is the same as the left-hand side. Therefore, I can write this result. D bar Q theta is also 0. Okay? Now, there's something important here, and that important element is the fact that this is for a reversible system. This is for a reversible system. For a reversible cycle. Right? This is now integrate for one cycle. Right? Now, why do we have this constraint of reversibility? I ask you to read about this. I hope you will pick it up right away. The reason that the reversibility is built in is because of this step. For PV system, if it's not reversible, you will not be able to express the work in terms of the state variable P. Okay, if you have non-reversibility, for example, when you have friction, you already know the external force. You will not be able to relate this external force to the internal pressure P of your thermodynamic system. Okay, the fact that you can equate these two means the reversibility is assumed. Okay, so for a reversible system, you have this result, and this is actually part of the closest theorem, which we will prove in a very general way. And this is a kind of a spatial way to look at this. This is for an ideal gas. Okay, and then you ask yourself, well, so what? What can we get from here? And now I will show you what you can get. Okay, I will tidy this for you later. Okay, I'm going to apply this result. I'm going to apply this last line, apply this to the Carnot cycle we derived earlier. Again, based on the ideal gas. Okay, this Carnot cycle, it's this one here. Right? So we go from A, B, C, D, A. This is a bit messed up actually. Why I don't know why it suddenly changed to a. Okay, this one should not be there. This one should be. Okay, so if you look at the previous one, this is how we go through. We went through this to get this result. So I'm going to show you a quick way to get this result. The one in the box. Okay, but still you should practice. This is the brute force method to get the result. And the elegant way to use the result is to look at this. Okay, what does it mean? This means the change of heat at this temperature, theta. Okay, so for the Carnot cycle, we have 4 segments. We have A to B is one segment, and A to B is an isothermal process, so the heat can enter. How much heat enters? We have theta 1, we have Q1 enter the system. And it enters at the temperature of the reservoir, theta 1. Okay, so this is for the process A to B. So this is the process A to B, from A to B. From A to B, Q1, the amount of heat entered is Q1. It enters at the temperature of Q1. Okay, B to C, what happens at B to C? B to C is adiabatic, so there's no heat enter, so you put a 0. Okay, and then what happens when you go from C to D? So B to C is here, and C to D again is isothermal, and this time heat leaves the system, so you have a minus sign. So I'm going to enforce this minus sign, otherwise we are going to get into trouble. Okay, and you leave the system to the reservoir. And what is the temperature of the reservoir? That is theta 2. And then you go back to from D to A, and there's an adiabatic process again, so there's no change of the heat. So this has to be 0. And why is this? This is basically the way to do this accounting around a closed loop. And the sum has to give you 0. Okay, so you can quickly see, I will put this for you. So I will have Q1, theta 1 is Q2, theta 2. And I get the desired result, this important result, Q1 over Q2 is theta 1 divided by theta 2, which is same as this. Okay, so I'm going to also box this for you. Okay, so let me make a bit of note to help you revise. So this is A to B isothermal. This is B to C. This is C to A. C to D. So this is isothermal. And then this is adiabatic. This is D to A. It's adiabatic. Okay, now this is cool. This is something I really like. Okay, next, about this Carnot engine, I have one more thing to say. This is the way to express the cycle in PV diagram. I don't really need to use P and V, right? I can use something else. For example, I can choose T, and I can choose something called S, the mysterious symbol, which you will see soon. What is this S? This S is entropy. And if I choose these two as my coordinates and draw the same process from A to B, so A to B is isothermal, so it has to travel horizontally, right? Isothermal, temperature cannot change. Okay, and this is at, this is, let me use theta. Okay, so this is at theta 1. Okay, and adiabatic, you will soon discover this also means the entropy cannot change. So this is a straight line, vertical straight line. So this is B to C. B to C is adiabatic. And now you know how to complete the rest. So this is isothermal compression. And then back to A. Okay, and dA is the adiabatic again. Okay, and here you get heat entering, and this is heat leaving. So I will label it for you. Okay, you have a rectangle. So a Carnot cycle on the temperature entropy diagram will be a rectangle. And that would be good, right? If you have, suppose I ask you to calculate the area enclosed by A, B, C, D, you know the meaning. And what is the meaning of that? Now the area enclosed by A, B, C, D here is this. I already told you, right? So this is the area enclosed by this. What is the area enclosed by this? A, B, C, D. And that is again, you go along the closed path, and that will be TDS. Imagine this to be a temperature. So this is TDS. And what does it mean? That is the key. What does it mean? So I'm trying to motivate you. And later when you see the results, you'll be like, I already know. Okay. Next. Okay, so we talk about Carnot cycle, we talk about Carnot engine, and Carnot is so important that you have so many things named after him. And there's the next thing, which is called the Carnot theorem. What is Carnot theorem? This is a very interesting theorem. Okay, so this is about the efficiency. As you can see, if I have an engine, A real engine cannot be 100% efficient. And not only that, there's a maximum efficiency you can achieve. And that efficiency is set by Carnot engine. Okay, so basically the statement of the theorem is this. So it says no engine operating between the same two reservoirs, between two given reservoir can be more efficient than a Carnot engine operating between the same two reservoirs. Okay, so this is some intrinsic limit. We know how to calculate the efficiency of a Carnot engine. This is what we talked about earlier. So you have this, this is basically related to Q1 divided by Q2. Okay, and if you have ideal gas, you can take it a step further. You can, once you know the reservoir temperature, you know the efficiency. And this is the limit, this is the upper limit. So if you go to buy a product, on the box, it says, okay, this product has an efficiency which is larger than the theoretical efficiency of a Carnot engine. Then you better be careful. You better don't buy this product because this product violates the law of thermodynamics. So that is to say you cannot build something which is more efficient than a Carnot engine. And how do you prove this? And to prove this, the idea is actually very similar to how we prove the equivalent of Kelvin and Clausius statement. You arrange some engines and you try to you come up with some arrangement, and the end result is you get either a violation of the Clausius or a violation of Kelvin. Okay, so you assume something. You assume now. What do you assume? The way to do this is you assume there's an engine which is more efficient than the Carnot engine. So I'm going to assume the efficiency of a hypothetical engine. Hypothetical because later we will know this is not possible. Okay, well, I'm going to assume this engine has an efficiency which is larger than the efficiency of a Carnot engine. Okay, and then I'm going to arrange this engine and then try to come up with some logical steps to get a violation of the second law. That is to say, I will either lead to Kelvin statement or the Clausius statement. I will either get to not K or not C. Then I know this assumption is wrong. Okay, so this is the way to do it. And again, we will need two engines. So I'm going to give you two engine. Here. Okay, and this is a very standard trick. By very soon you'll be very tired of this. Okay, this hypothetical engine H is here. So I'm going to have an H here. And then I'm going to drive with a Carnot engine, which I know very well. And this is again the same temperature, So eventually, you know what I want. I want to make them to be the same reservoir. Okay, let's look at this engine. I'm going to label it before we do the calculation. This engine is fine. We can have this engine. You see, this is a legitimate arrangement. I can have this engine here, right? I take some heat here, and then I get some work. I have some waste. And likewise, I have my Carnot engine, which I will label QCN1, but this too messy, so I'm going to suppress the n. This is Q Kano and Q Kano 2. And what do I get? I will get some work like that. Okay, so this is the setup. This is what I want to analyze. I'm going to analyze these two engines. And my assumption is this. My assumption is this. Okay, and how do you define the efficiency? You define the efficiency as what you get divided by what you pay. So in this case, I will have this result, C1. Okay, so this is just the definition of the efficiency. If you look at these two engines separately, you can get two more lines. So if you look at them separately, you know what is WC. WC is the difference between QC1 minus QC2. And WH is H1 minus QH2. Okay, so this I'm looking at these two engines independently. Okay, what is the trick now? Now I want to, I have these two engines which I know they are good engines. I can have them, no problem. And now I'm going to start to play with the engine. So how am I going to do it? I'm going to do the following. I'm going to take this engine so I'm going to run the Kano engine backward because I already told you Kano engine is reversible. So I can run it backward. If I run it backward, look what happened. How do I run it backward? So now please follow me. Try to follow me as closely as possible. I don't want to write everything again and again. So I'm going to run this engine, the one on the left, backward. Backward means I will flip the direction of the arrow. Okay, I'm going to do just that. So I'm going to flip the sign. This was down, this was down. So I'm going to flip it upward. Okay, and for the work, this is pointing to the left. Okay, this is pointing away from the engine. So if I run it backward, I have to have this work term, this arrow pointing towards the engine. Okay, so I'm going to do just that. Okay, so the work, I'm going to arrange it such that this is pointing towards the engine. Okay, so this is my WC. Let's make it longer. Okay, are you with me? So my WC is here. So which means in order for this engine to be driven backward, I have to supply some work. And I can play the trick. I look at the engine on the right. That gives me the hint. I know where to supply the work. I can use the hypothetical engine, this one. I can fit whatever work here into here. I can arrange them such that these two are the same amount. Okay, so if I take one more step for you, this is WC, right? And now what I'm going to arrange is I'm going to fit all the WH to the Kano engine, to drive the Kano engine, and I'm going to adjust the rate such that in the given interval, these two will be exactly the same, which I can do. Okay, once I do that, of course, I will have some equality to link up these Qs. Okay, so I'm going to do just that. What I say earlier, I'm going to fit all these like that. Okay, I'm going to take this pipe or whatever, this outlet, and connect to the input of Kano. Okay, so this means WC. I have demanded these two to be the same. Okay, that's all the setup I want. Okay, so if you have WH and WC to be the same, now you look at all this line, as simple as this. You come back and look at this. Okay, so let me label 1, 2, and 3. And this is 4. This is a new setup. 4 is the new setup after I do this manipulation. So from here, 1 will give me QC1 has to be greater than QH1, right? Because these two are the same, because of 4. Okay, and then from 2 and 3, from 2 and 3, what do I get? I will have QC1 minus QC2 is the same. Now these two now becomes the same because of 4 H2. Okay, and I want this is not too useful for me, so I want to rearrange it a little bit. So I bring this all the 1s to here and all the 2 to the other side. So this will be QC2 minus QH2. Okay, so from here, this line, I get this line. But QC1 is greater than QH1, right? So this minus this is positive, and therefore this has to be positive. This is important because this will determine how I draw my arrow later. Okay, so I basically have everything I need to construct the composite engine. So what I do is the same trick. I'm going to view this as the composite engine. The internal engine, internal path doesn't matter. I will just imagine this to be a huge engine. And the internal structure, I don't care. All right, so which means there's no more output from here. Okay, so I end up having this, only this line. Now, one of them is not allowed. One of them is not allowed. Which one is not allowed? If the arrows are pointing upward, it's not allowed because you have the heat transfer from cold to hot. But if the arrow is pointing downward, it's fine. Okay, so we need to really see this is up. Okay, so how do we draw this as up? Look at, if you want to draw this as up, so QC1 has to be positive, and this has to be this down will take a minus sign. Okay, now this arrow is indeed the same as the direction of QC1 if this is positive, if this difference is positive, which we have shown to be positive. So this is fine. And likewise, for the bottom, we have QC2 here, QH2 there. So we have QC2 minus QH2. And it's also positive, so it's following the direction of QC2. This is also fine. Okay, and what is this engine? This engine is not C. And therefore, this is a contradiction. Where is the problem? The problem is assumption. This assumption cannot be correct. So therefore, this cannot be greater than this. So the hypothetical engine cannot be more efficient than the Carnot engine. And the statement then is the hypothetical engine will have an efficiency which is at most the efficiency of the Carnot engine. Okay, now this is cool. The only assumption is the Carnot engine is reversible. Now, if I assume my hypothetical engine to be reversible as well, I can repeat the same thing, right? And that will flip the sign of the inequality. Okay, so if I have, if additionally, so if H is also reversible, up to now, I didn't say anything about the hypothetical engine being reversible. up to here. And now if I also demand this, I can repeat the same process, and that will give me this. Okay, I have this additional requirement. So remember, be careful. This is the additional requirement. This has to be satisfied together with this. This alone cannot be true, otherwise we are in trouble. Okay, so this is an additional requirement on top of this. So if H is also reversible, the conclusion then is the efficiency has to be identical. So this is called the Carnot's theorem. Okay. All right, so we learned a lot about Carnot cycle. We learned a lot about Carnot engine. On Wednesday, we are going to use it to obtain the thermodynamic temperature. Okay. All right, thank you very much. That's a good point. This is a good point to stop.